Right, welcome back everyone. So we continue today with the last subsection in this long section on Schwarzschild spacetime. And the topic we still have to discuss is the light-like geodesics. So we did in some detail last time the time-like geodesics. So today we have light-like geodesics. And I will concentrate on things which are relevant for black holes. This means for light rays which comes close to the horizon in Schwarzschild spacetime. So one of the main goals of today's lecture will be to understand what we mean when we speak of the shadow of a Schwarzschild black hole. Okay, so geodesic equation, we already had the geodesic equation. So this is, now we have light-like geodesics, we parameterize them by an affine parameter. So for light-like geodesics we use proper time, and we write for d by ds, we write just the dot. And then the geodesic equation is d by ds now, not d by d tau, dl dx mu dot minus dl dx is 0, where L is the Lagrangian for the geodesics, which is, maybe I should write the arguments. Oops. So Lagrangian depends on the points in the base manifold and in the tangent space, and this is 1/2, no bracket, x mu dot. And now we have light-like geodesics. This means we have g mu nu x mu dot equal to 0. So that's the difference in comparison to the time-like geodesics. Yeah, there we had minus c squared here. And if we were interested in space-like geodesics, we would have something positive here. Okay, so the set of equations we will need is, as in the time-like case, it's only 3 equations because we can restrict to the equatorial plane, just because of the symmetry. This means we have theta equal pi half and c dot equal to 0, and then the Lagrangian is just 1/2 minus 1 minus rs r over r c squared t dot squared plus r dot squared 1 minus rs over r, and from the angular part we only have r squared phi dot squared because of these two assumptions. Okay, and well, we could write down all 3 components of the Euler-Lagrange equation, but actually, as we have also this equation in addition, it suffices if we consider only 2 of them, as in the time-like case. So I write only the t and the phi component of the first equation. So this gives me d by ds. If I take the derivative of this Lagrangian with respect to t dot, I get a minus, 2 cancels 1/2. Minus 1 minus rs over r c squared d dot, minus partial derivative, there's a mu missing, with respect to t, there is no t. So it means minus 0, it's 0. And this implies that the thing in the bracket is a constant of motion. Yeah, its derivative is 0. So it implies that the quantity 1 minus rs over r c squared t dot is a constant of motion, and that's what we denote E, as in the case of the time-like geodesics. And this is the same equation which we had for the time-like geodesics, where we labeled it A. And then we have the phi component, d by ds. By the way, in the written lecture notes there was a stupid misprint. When I calculated the phi component gives r squared times phi dot. And in the script, for some strange reason, the r squared is in the denominator. I don't know what made me write such a stupid thing. So I will correct this when I send around the next chunk of lecture notes. And again, there's a 0 because the Lagrangian is independent of phi. So we have another constant of motion, which we denote L. And this is our equation B. And then the third equation, that's now different from what we had for the time-lag case because we have the 0 here. The third equation is now minus 1 minus RSR C squared T dot squared plus R dot squared divided by 1 minus RS over R plus R squared. Phi dot squared is 0. That's our new equation C. So we have 3 equations for the 3 quantities T dot, phi dot, and R dot. So we can determine the orbits from these 3 equations. There's another equation which is valid. That's the R component of the Euler-Lagrange equation, but that's dependent. It doesn't give any additional information, as you may check if you like to do so. So actually, when we talked about time-lag geodesics, we first considered the radial geodesics. That I will not do for the light-lag case because we have already done it when we introduced the Eddington-Finkelstein coordinates. So here I will just assume that we have non-radial geodesics. And for non-radial geodesics, I can use the coordinate phi as a coordinate. So if where the parameter s has no physical meaning anyway, yeah? So it's just one way of parameterizing the curve, and if I'm just interested in the orbit, in the geometric shape of the orbit, I can equally well use the coordinate phi. This doesn't work for radial geodesics, of course, because then the phi is constant, yeah? But it works for any non-radial geodesics. So use phi as a parameter. So then we are interested in an equation for r as a function of phi. R as a function of phi, and we get this from these 3 equations by inserting A and B into C. So insert A and B into C. Then what do we get? So I write C again. Minus 1 minus RS over R. Oh, wait a minute. Maybe first I divide by phi dot squared. Maybe that's a better idea. I jumped one step ahead. So I divide C by phi dot squared. Because then I get here R dot squared divided by phi dot squared, and that's the R by the phi squared. So this gives me the orbit equation. So then I have what? Minus 1 minus RSR C squared T dot squared over phi dot squared. 1 over 1 minus RS over R dot squared phi dot squared plus R squared is 0. And now I insert for T dot squared and for T dot and phi dot the expressions from A and B. So let me see if I can do this in my head. So T dot squared, I insert this expression. So this is E squared divided by this thing squared. E squared divided by C to the 4, 1 minus RS over R squared. And then I divide by phi dot squared. Phi dot squared is L squared divided by R to the 4. Okay, that's the first term. And for the second term, I just write this. R dot divided by phi dot is, by the chain rule, dr by d phi. So R squared is 0. And what I have to do, well, there are a few terms cancelling. This cancels. This cancels. We'll have to squeeze it here. Oops. So I get, it's supposed to be a D. dr by d phi squared is what? I multiply everything with 1 minus rs over r. And then I get a big bracket. So this comes now to the other side, so it gets a plus sign. E squared r to the 4 divided by c squared L squared times 1 minus rs over r. And then minus r squared. Okay, and I think I multiply this out. And I get e squared 4 c squared L squared. Oh no, this cancels. This cancels. And then I have minus r squared plus rsr. And that's my orbit equation. Okay, so that's the equation for light rays. You see an important difference in comparison to the time-like geodesics is that the constants of motion E and L only occur in the combination E divided by L. So there's only one parameter, yeah, namely E divided by L. For the time-like case, we had E and L in different terms, so it was a 2-parameter family. And here we have only a 1-parameter family. Yeah, the reason is that if we talk about light rays, we have no room for choosing the speed of the object. Yeah, the speed is fixed just by the property that we are talking about light. Okay, so what can we do with this equation? Well, we can discuss all kind of motion of light rays. So the first thing we want to discuss is circular light rays. So is it possible for a light ray to stay on a circle r equal constant? Yeah? And well, obviously then we must have dr by d phi equal 0 and also the derivative of this equal to 0. So we must have, how do I write this? We must have 0 must be this expression, e squared r4 c squared L squared minus r squared plus rsr, because the r by d phi is 0. But also the derivative of this thing must be 0. Because if I take the derivative of this side, and if the function r is constant, then I still have a 0. Yeah? So I also have a 0 for the derivative of this. This equation alone doesn't help, because we have it doesn't fix the radius for which circular light rays exist, because we still have the E over L in it. And we need a second equation. And the second equation is found by differentiating this. Let me see if I can differentiate this. 4e squared r cubed, c squared L squared minus 2r plus rs. And from these two equations we can eliminate E over L. And then we get an equation for the radius at which circular light rays exist. So in order to eliminate the E over L, I think I multiply the first equation with a 4, and then I take the difference. Oh no, and I multiply this with r, because then these two terms cancel. Then I have 0 is 0, minus 4r squared plus 2r squared is minus 2r squared, plus 4rsr minus rsr is plus 3. rsr, and lo and behold, I get the correct result, because this implies that r must be 3/2 rs. So at this radius, at 3/2 Schwarzschild radii, we have a circular light ray. I think most of you knew this before, but in any case, that's something one should know. So we have the following situation. So if I plot this, I have here my black hole. So here is the horizon, Rs. We know already that a lot of things is going on near the horizon. If I cross the horizon, I cannot come back. And if I approach the horizon, I'm infinitely redshifted for a distance observer. But now we have learned that there's also something interesting at 3/2 Rs. So that's 3m in natural units, right? If I set g equal to 1 and c equal to 1, then Rs is 2m, and the light sphere is at 3m. And what we have just calculated is that if I send a light ray with this initial direction, tangential to this circle, then it will stay on this circle. And this means that if I am situated at this point, of course I need a rocket engine in order to stay there, right? If I just go there and then let me let me float, then of course I would be drawn into the black hole. But if I have a rocket engine, I could stand still here at this point. And if I look in the tangential direction, then I would see the back of my own head, right? Because the light ray goes around from my head along this circle and then enters into my eye. And if I build a little tunnel around this circle and I look into this tunnel, then the tunnel appears perfectly straight to my eye because the light ray stays on the axis. Is the question?
This is an unstable orbit.
This is, yes, I come to this in a minute, yeah. But this is irrelevant for the things I've just mentioned.
But if the light escapes during the time that it rounds around the black hole, then you can't see it.
Well, if I have a lamp or some light source at the back of my head, then it will emit light rays in all possible directions. And there will be a certain bundle of light ray which stays around the central axis. So the neighboring light rays will spread. That's true. Yeah. So and finally, if you follow them, further in time, then they will spiral away from this circle. That's true. But there are light rays which stay precisely on this circle, and there's a bundle of light rays around this which will spread, but nonetheless which will be centered around this axis.
Well, but then the question is, what's the mean number of revolutions of light that is possible on this unstable orbit before the light?
Yeah. Well, but that's irrelevant for what I've just said, because I've thought of the situation that I have a lamp at the back of my head which is continuously emitting light. Yeah. So what you are asking is if you have a light flash, you just send out a light flash. For how long will there be a measurable quantity of photons on the circle? That's a different question. But what you just said is in fact very important. The fact that this is unstable, this will play a crucial role in a minute when we discuss the shadow, because it is that's the reason why it's possible to spiral towards this curve. Yeah. So what do we mean if we say stable or unstable? If I send the light ray exactly tangential, then it would stay on the curve. That's what we have just calculated. The question is, what happens if I do this at a slightly bigger or at a slightly smaller radius? And there are two possibilities. Either the light ray would oscillate around this curve. Then we would say this orbit is stable. Or it would go away. So in this direction or here in this direction. Then we would say it is unstable. And actually what happens here is that it is unstable. If you want to check this analytically, you would have to consider the second derivative. Yeah? For the time-like geodesics, we have discussed the question of stability. Actually, we could do this as a little exercise. I was planning a problem about the circular light orbit anyway. We can check in the tutorials that it is unstable. Yeah, you just have to check the second derivative of this thing. So, and now if we have found this result, we know that the light ray which is sent, well actually I overdid it a little bit, it works in this way. Yeah, it spirals with an increasing radius. And if we have this information, then in the Schwarzschild spacetime we know that the time direction is invertible. Yeah, if I change t into minus t, I have the same metric. Yeah, because I have no cross terms in the metric. Here's a metric. You see t dot occurs only in a quadratic way. So if I replace t by minus t, this means t dot by minus t dot, it's exactly the same thing as we had before. So it will be different in the Kerr metric. In the Kerr metric we have a term t dot phi dot. So if there we reverse the sign, then we get something different. But here for the Schwarzschild spacetime, which is static, there's the time direction. There we have a symmetry with respect to the time direction. This means if this light ray exists, which is parameterized in this way, then also this light ray exists, which is parameterized in the opposite way. And then we get a light ray which spirals asymptotically towards our circular light orbit. And the fact that this is possible, this is crucial for the construction of the shadow. I will come back to this in a minute. So if we had a stable light orbit here, if this would be stable, then it would not give rise to a shadow. Okay, now I lost the thread a little bit. What did I want to say? We had calculated. Oh yes. Maybe you can also do in the tutorials another thing. You might say where there are other methods to find out that this is actually not a straight line but a curve. Yeah. So if you just look in this direction, you have the expression it is a straight line, although it is a circle. You might think there are maybe other methods to find out that it is a circle. For instance, you could use a gyroscopic compass. Yeah? You could take a little gyroscope which points in a particular direction, and if you move in a straight line, then you would expect that if you start tangential to the direction with the axis of your compass, then it will stay tangential to this axis. And if you move on a circle, then you are used to the fact that then it will deviate. But if you do this along this circle, actually it will not deviate. It will also stay always tangential. This, I'm not sure if we can do this easily. So that would be one method which I just mentioned here, that also with a gyroscopic compass you cannot find out that this is not a straight line. And then there's another method that you measure the centrifugal force. Yeah? So this is an orbit for light rays. So if you want to move in free fall along this circle, then you would have to move at the speed of light, which of course you cannot. So in free fall, without an engine, you cannot move on this circle. But if you have an engine, then of course you can do this. Yeah? So if you have an engine, you can arrange things in such a way that you move, say, with constant velocity along this circle. You also can do this at bigger radii and at smaller radii. And what you usually feel if you move with an engine on a circle, think on a roller coaster or something like that, yeah, where you are strapped in your car and now you go around in a circle in an accelerated way. Yeah, you are accelerated in the radial direction. Then what you feel is that your stomach wants to move freely. But you are strapped to the car, so the stomach cannot go away, fortunately, and you feel a relative motion of your stomach with respect to the rest of your body, and that's what makes you feel sick. Yeah? So you feel the centrifugal force if you are sitting in a roller coaster car. And now you do the same thing at this circle. You go around with a constant speed, and you don't feel anything. There is no centrifugal force. I think we can do this in an exercise. That's not too difficult to calculate. If you do it at a bigger radius, then we have the usual impression that that we have a centrifugal force which is pointing outwards. Yeah, so that the centrifugal force wants to push us outwards. If you do it at a smaller radius, the centrifugal force wants to push you inwards. Yeah? So if you do it if you go around at a smaller circle, you have the impression that this is the outward direction, yeah? Because your stomach wants to go in this direction. And if you do it precisely at r equals 3/2 rs, you don't feel anything. So also your stomach tells you are moving in a straight line. There's no circle. So that's quite an interesting phenomenon. Okay, so that's a light orbit. Then the second thing which we want to calculate is the bending angle. So and maybe I should have stressed this happens only at this radius. There's one particular radius where we have this circular light orbit. At no other radius is it possible. We have shown this here. At no other radius is it possible to have a light ray staying on a circle. Oh, I forgot something. I should determine the E over L for this orbit because I need this later. So every orbit has a particular quotient of E over L, and we will need the value for this quotient for this particular orbit. So with r equals 3/2 rs, we can insert this expression into either of these two equations, and we get the E squared over L squared for this expression. So we have 0 is E squared over C squared L squared r to the 4, and r to the 4 is 3/2 rs to the 4 minus r squared. and RSR. And the whole thing is 0. So let's calculate this. This is E squared over C squared L squared. So can I do this in my head? I think I can cancel a 3/2, right? What can I do? A 3/2, actually I divide by 3/2 RS squared, right? So then I have 3 to the 3, this is 27 if I'm not mistaken. 3 times 3 times C, 3 times 9 is 27, right? Okay. 2 to the power 3 is 8, and I've divided by RS squared, so I have RS squared left. And here I have minus, I've divided by 3/2, so I have only 1 3/2. And I have divided by, what's with the power? Something is, no, I think it's correct. I think it's correct. 3/2. And that's it. And here I have plus 1, right? Oops. So I have E squared over C squared L squared is what? This is 1/2. It is plus 1/2. Is that true? It's 1/2. And I have 8. So from the 8 we only have a 4. 8 divided by 2. And here I have a 27. And here I have an RS. Here I have an RS squared. That's it. Is that true? I hope it is. We will need this later. So this is the value, the constants of motion E and L take for this particular circular light ray. And please watch that I don't erase this equation because I will need it in a few minutes. Okay. So now I come to the bending angle. I think everyone knows the formula for the bending angle in the weak field approximation. That's what Einstein did in 15, around that. But there is an exact formula for the bending in the Schwarzschild spacetime, which just gives the bending angle in terms of an elliptic integral, which isn't too bad. So it's not an elementary formula, not a formula in terms of elementary functions, but it's a formula in terms of an elliptic integral, which is equally well. And I want to briefly derive this formula, and then we will plot it. And this will give us an important hint in which way we will approach the phenomenon of the shadow. So for calculating the bending angle, we are now interested in the following situation, that we here have our black hole, and then a light ray comes in and is deflected by the black hole. It comes in from infinity and goes out to infinity. And what we want to calculate is actually this bending angle. How do I want to call it? I should use the same letter as I have in my notes. Yeah. So you see, this is an axis of pi. So this is no. This angle is what I want to call delta. Then I have here, if I consider the whole range of phi coordinates, which is swept through by the light ray, then I have this here. This is pi plus delta. And the light ray is characterized by a minimal radius, which I denote Rm. Yeah? So depending on the angle under which I send my light ray towards the black hole, it will reach a certain minimum radius, which I denote Rm. And of course the delta will be dependent on this Rm. This was a plus here. Okay, that's what we want to calculate, and all the information is coded in this equation for the orbit. So we have the phi is what? It's plus minus the r divided by the sink on the right hand side. e squared, oh, this was d phi by dr squared, so I have a square root here. E squared r to the 4 to the 4 c squared L squared minus r squared plus rsr. So you see the orbit equation parameterizes the light rays by E over L. Here I want to parameterize it by this minimum radius Rm. So I need to know what's the relation between E over L and Rm. So because we have d phi by dr, no, the other way around, dr by d phi must be 0 at r equal Rm. And this implies that this expression must be 0 for r equal Rm, right? The r by d phi is just this square root, so we must have e squared over c squared L squared Rm to the 4 minus Rm squared plus Rs Rm is 0, and this gives me e squared over L squared in terms of Rm. L squared, so this is equal to what? It is something divided by Rm to the 4, and here I have Rm squared minus Rs Rm. Okay, it can be simplified a little bit, but anyway. And so this is the expression I can insert for E over L. And then I can integrate this over the whole orbit, and then I get the formula for the bending angle. So I get d phi is plus or minus dr divided by square root. And now I insert for e squared over c squared L squared this expression. So I have an Rm squared minus Rs Rm times r to the 4 over Rm to the 4, and the rest I just copy, minus r squared plus Rs over r. So you see that's an elliptic integral, right? If you have under the square root something which is of third or a fourth order, then we call it an elliptic integral. Yeah, if it is quadratic, if we had only this term, this would be an elementary integral. Could express it in terms of, I don't know, arc sine or something like that. If you have higher orders, if you have a fifth power or something like that, then we call it a hyperelliptic integral, which can also be handled quite properly. Okay, so here we have an elliptic integral, and we just have to integrate this now over the whole orbit. So if I want to get my angle delta plus pi, this is the phi coordinate integrated over the whole orbit. Then my light ray comes in from infinity. There, this is decreasing. The r coordinate is decreasing, so I have to choose the minus sign, right? The minus sign, and the r coordinate goes from infinity, sorry, that's a plus, from infinity to Rm. Yeah, it is this leg. I start here and I integrate up to the point of closest approach. On this leg, the dr is negative, r is decreasing. I begin at infinity and I end at Rm. And then I have the second integral. There the r is increasing, so I have a plus sign. I begin at Rm and I end at infinity. And that's what I have to calculate. Root Rm squared minus Rs Rm r to the 4 Rm to the 4 minus r squared plus Rs r. Oh, I think one can simplify this a little bit, right? We can take an Rm minus Rs out of the bracket. Maybe I should do this. Anyway, you see that's the same integral, right? If I interchange the boundaries, then the minus becomes a plus, and I get 2 times the same integral, which is obvious from the symmetry of the problem, right? So the phi, the increase in the phi coordinates is of course on both legs the same. So I get 2 times integral from Rm to infinity. And maybe I now simplify this a little bit. I think I can here take an Rm minus Rs out. And then 1 Rm cancels against 1 power here in the denominator. So I have this. And here I can also write it in this way. Minus R minus Rs. Maybe that's a little bit nicer. And yeah, that's the integral you have to evaluate. And if you do this, then you can plot this angle. And what you get is, of course, if the Rm is very big, then the deviation from pi will be very small. Then the thing will be more or less a straight line. And if you come closer to the center, so if you choose your Rm smaller and smaller, then this angle delta will become bigger and bigger. And if you evaluate this integral, what you get is actually something like this. So if you plot this, so you plot the delta as a function of Rm, then yes, you have, so delta is an angle, so it will become 2 pi, 4 pi, 6 pi, and so on. So if Rm is very big, delta is very close to 0, so it will come here in this way. And then it will become bigger, bigger, and bigger. And if you, by the way, there is the integral is a little bit delicate, because whatever the value of Rm is, this denominator has a 0 at r equal Rm. Yeah? So at the boundary of this integral, the denominator has a 0. So the integral must be evaluated with a little bit care. But this can be done, and for all values Rm bigger than 3/2 Rs, actually you get a finite value. But if you approach the light sphere, which we have still on the board there, r equals 3/2 Rs, then this integral will approach infinity. So when we have here 3/2 Rs, here's the horizon. We are still above the horizon. Here is Rs. If you approach the light sphere, then this will go to infinity. And what does this mean? Well, it means for a certain value, the bending angle delta will become 2 pi. What does this mean? It means that the light ray makes a full turn around the center. Then it will become 4 pi. This means the light ray makes 2 full turns around the center, 6 pi, and so on. So that's what happens if a light ray comes close to the black hole. It is forced into rotating around the black hole. So if you are far away from the center, then we have the situation we know from the solar system. Yeah, that we have a certain bending angle, which, well, for a light ray grazing the surface of the sun, it is just 1.7 arc seconds. Yeah, tiny, tiny angle. So we are far, far away from the Schwarzschild radius of the sun, which is just 3 kilometers. And the radius of the sun is, what is it? 700,000 kilometers? Something like that, I think. So definitely much more than 3 kilometers. Okay, but if we have an object which is, which is much more compact, where the physical radius is, in comparison to the Schwarzschild radius, much smaller than it is for the sun, then we have these big bending angles. And this phenomenon that the bending angle becomes infinite, this happens not only for black holes. Black hole means that we can actually, the vacuum solution extends up to the horizon. Yeah, the horizon is really present in the vacuum region. We could imagine a star which has a radius between Rs and 3/2 Rs. That's what's sometimes called an ultra-compact star. So this would still be not a black hole. There's no horizon. It's not a collapsed object, but it would already show this phenomenon of an infinite bending angle, and it would already display this circular light orbit. If such ultra-compact stars exist is a question of debate. Yeah? So you can check that if you want to do it with ordinary matter, say with a perfect fluid, with an ordinary equation of state or something like that, that it doesn't work. So either the pressure becomes infinite in the center or some other pathologies will occur. But you can think of more exotic kind of matters. So there was a model which was discussed in the last 10 years or so quite intensively, which is called a Grava star. Yeah, so people cooked up a kind of quantum matter which is arranged in a certain shell, and then this could have a radius, as I said, between Schwarzschild radius and 3/2 Schwarzschild radii. But later there was a claim that such a thing cannot be stable. I'm not quite sure what's the present status of this discussion. So what I want to say is that these ultra-compact objects are hypothetical. Up to now there's no evidence that stars exist with a radius between Schwarzschild radius and 3/2 Schwarzschild radii. But if they do exist, they would have a very similar influence on light rays as a black hole. Actually, it would be very difficult to distinguish them from black holes. For these reasons, these objects are also sometimes called black hole imposters. Yeah? So things which pretend to be black holes, but actually they are not black holes. And a Grava star is one of the main candidates for a black hole imposter. Of course, we could easily distinguish such an object from a black hole if it would have a shining surface. Yeah? What a black hole does not have. A black hole doesn't emit light by itself. If you have a star with a radiating surface, then of course we could see this object. But you might think of an ultra-compact object which is dark. Yeah? Then it would be very difficult to distinguish it from a black hole. Okay, so here we have this phenomenon of the bending angle becoming infinite. Yeah, so and this is a consequence of the fact which we have discussed before, that this light orbit is unstable. Yeah, because what is the light ray doing with such a big delta? If we are here or even further up, what it does is it comes in from infinity and then it starts spiraling. And it goes closer and closer to the light sphere and makes more and more turns. And eventually, then, maybe as long as the delta is finite, it will turn back. It will then spiral back again. But there's an asymptotic limit, and this is reached when we have Rm equal to 3/2 Rs. This is no longer an orbit which comes in from infinity and goes out to infinity. It's an orbit which comes in from infinity and approaches the light circle asymptotically. And okay, that's what we can learn from this discussion. This was the bending angle, and now I come to the topic I've already announced a couple of times, namely to the shadow of a Schwarzschild black hole. So again, we consider the situation that we have our black hole, horizon at r equal Rs. Then we have the light sphere at 3/2 Rs. And now I assume that I'm an observer situated at a certain radius coordinate Rho, at a certain distance, certainly not inside the black hole, in the exterior region, of course. And the question is, in which way sees this observer the black hole? Well, it depends, of course, on where the light sources are. Seeing something means receiving light from light sources. So in order to answer this question, what the observer sees, we need to know where the light sources are. And what we will assume, if we discuss this notion of a shadow, is that there are no light sources between the black hole and the observer. But anywhere else, wherever you like, behind the black hole, behind the observer, here in this way, we know that the black hole bends the light in a way that it turns back. So also a light source situated here could be seen with a light ray which comes from this direction at the observer. Yeah? So we assume that we have light sources everywhere, but not between the observer and the black hole. So here there are no light sources. Actually, if we think of a realistic black hole, maybe the thing in the center of our galaxy, then unfortunately there's a lot of matter here in this area, because our black hole certainly is surrounded by some kind of matter, an accretion disk, maybe also a corona, maybe also a jet. So there is matter between us and the black hole. But for this theoretical discussion, let's assume there's no such matter. And we will now discuss what does an observer see. Is there any suggestion, any intuitive idea what the observer would see if we have light sources anywhere, but not between us and the black hole, and then in this direction there's a black hole? What would I see? What would you expect? The black hole itself, of course, is dark. That's why it's called a black hole. It doesn't emit light. So one would expect to see what? A black disk. Yeah, a black disk. And actually what we want to calculate is the radius of this black disk. So in order to do this, well, whenever you want to know what an observer sees, what we have to discuss is what are the light rays which arrive at this observer. And because the light rays arrive from the past, it is convenient to start at the observer and parameterize them in a past-oriented way. So we consider all light rays, this means all light-like geodesics, which start here, which are parameterized in a past-oriented way. Yeah, so when the parameter S increases, then we go into the past, because we want to receive a light ray, which comes to us from the past. And we want to know if this light ray actually is seen as a bright spot at this observer. This means that if I follow this light ray, then it must reach one of my light sources. Yeah? So I send out light rays into the past. They will be sent out under a certain angle theta with respect to the radial line. We are in a spherically symmetric space-time, so we have a distinguished radial direction at every position of the observer. And then it depends on this angle theta if we have light, darkness or brightness. So we see if the angle theta is big, then this light ray will go out to infinity. Maybe it will be deflected by the black hole, and then it will go out to infinity again. If we do it at a smaller angle, then it will go towards the horizon. Actually, in our Schwarzschild coordinates, it will never reach the horizon. Yeah? Remember, if I follow a light ray, which approaches anything which approaches the horizon, then it will never reach the horizon at a finite coordinate time t. Yeah. So, but what it can do is that it can approach the horizon in these Schwarzschild coordinates asymptotically, and that would obviously would happen for small angles. And then there is a limiting case, a boundary case between the light rays which go to the horizon and the light rays which go back to infinity again. And that will be a light ray which spirals towards our light sphere. This will be the borderline case which determines the boundary of the shadow, right? So the assumption is that these light rays which go out to infinity again, somewhere on their way will meet one of our light sources, because we have light sources everywhere. But the ones which go to the horizon, they will never meet a light source, because we assume that here in this region there are no light sources. And so here for this initial direction, for the small angles, we have darkness. For the big ones, we have brightness. And the borderline case is one which approaches a light circle asymptotically. And that's what we have to calculate now. And, well, in order to do this, I denote this here by delta y and this by delta x, just to get a handle on this angle theta, to characterize it in terms of my orbit equation. And then obviously the angle, or rather the tangent of the angle theta is the limit of delta y divided by delta x for delta x to infinity. And well, these lengths, delta x and delta y, well, of course I have to measure them with my metric. So I have to read the length measure from the metric. So this is the length where only the r coordinate varies. Yeah, phi is constant. So I could write this as dr. And this here is a direction where, well, in the limit, only the phi coordinate varies. Yeah, only the phi coordinate varies. And this is a test length r d phi. And I am at radius r equal rho.
I think delta x should go to 0.
Oh, sorry. Yes, of course, sorry. Okay, and these expressions I can now read from the what did I do? Sorry, this was one step too fast. I said that I have to measure this with the length of my metric. Yeah. So this is a length which where only the r coordinate varies, but of course I shouldn't use the Euclidean length measure for this. I should use the length measure which I can read from my metric. And I hope you remember what, I don't have the Schwarzschild metric on the board, but I hope everybody remembers that the dr comes with, the dr squared comes with a 1 minus rs over r, so I have to take the square root here. Okay, so this is the length in the r direction measured with the metric. Yeah, this is dr divided by the square root, because I have in the Schwarzschild metric I have this metric coefficients, and for the angular measure there it is the same as in the Euclidean case. I have just the r squared in front of it. Okay, so this is what is this now? It's 1 minus ro root 1 minus rs over ro dr by d phi at r equal ro. And the r by d phi, I'm talking about light rays. Yeah, I'm talking about light rays. The r by d phi, of course, can be written, can be read from this orbit equation. So I have 1 minus ro, root 1 minus rs over ro. The r by d phi is the square root of these things which I have there. E squared r to the 4, and it's ro now. Yeah, I am at the radius coordinate r equal ro. The index O stands for observer. C squared L squared minus ro squared plus rs ro. That's it. So this is for any possible value of E divided by L, which parameterizes my light rays, the corresponding angle theta. And now the boundary of the shadow is given by, any question?
Well, if we are talking about this delta y over delta x, shouldn't it be the other way around? So delta y is r d phi, and delta x is dr over the square root.
Oh yes, thank you. I confuse these two distances. Yeah, it's just the inverse.
Them, so
No way. Is that okay? I think this equality sign is correct, right? This is really the tangent of theta, dy, yes. And then I just inserted them the other way around. So I think that's correct now. Okay, so this gives me the angle theta for any light ray parameterized with this constant of motion E over L. Now I'm interested in the angle theta which corresponds to the light ray that spirals towards the circle at 3/2 rs. And that's the reason why I calculated the constants of motion which is associated with this circle. Because if a light ray spirals asymptotically towards another light ray, then the two light rays must have the same constants of motion. Is that clear? Because they become more and more tangent. Yeah? And the constants of motion are related to the initial condition, to a tangent at any point. But if the tangent in the limit become equal, then the constant of motion must be the same. So the limiting, the constant of motion of this limit circle must be the constant of motion of the light ray which gives the boundary of the shadow. Yeah, the light ray which just spirals asymptotically towards this circle. So, so theta 0 is the radius of the shadow. Corresponds to E squared over C squared. L squared is this expression here. Oops. 4 over 27 rs squared. And now I can erase this. And continue on this board. So today we speak of the shadow of the black hole. There are older articles where this word was not used, where people spoke of the escape cones. Yeah, what we are calculating is a cone which determines the boundary, the boundary of the angle for a light ray so that it can escape to infinity from a certain position. So if you find the word escape cone for light in a certain space-time, then that's exactly the same as what we nowadays call the shadow. And actually the first person who did the calculation we are just doing was John Singh in the 1960s. And the title of this paper was something like Escape Cones in Schwarzschild Spacetime. So we can now calculate the tangent of theta naught. Just by inserting this expression for E squared over C squared L squared. So this is R naught root 1 minus Rs over R naught. I hope this becomes readable in a minute. Now I have to insert this expression for, oh, there's something wrong with the units. Here I have a power 4, here I have only a power 2. This cannot be true. Oh, it can. Yes, of course. The whole expression is quadratic in R. Everything is fine. Everything is fine. So I have 4 R naught to the 4 divided by 27 Rs squared minus R naught squared plus Rs RO. Okay, can be written in a nicer way if we express it in terms of the sine instead of the tangent. So let me write sine squared of theta naught. So the sine is what? Oh no, let me write it in this way. That's better. This is tangent is sine divided by cosine, right? And cosine is 1 minus sine squared. And now let's solve this equation for the sine. Oops. So if I multiply this with the two denominators, then I have R naught root 1 minus Rs over RO root 1 minus sine squared theta O is sine theta O times this square root O to the 4 27 Rs squared and this RO squared plus Rs RO. Let me see. I think I should square the whole thing so that I can solve for sine squared theta, right? So I have, okay, I have R naught squared minus Rs RO 1 minus sine squared theta O. And here I have sine squared times the radicand minus RO squared plus Rs RO. And now I collect everything with sine squared on the right hand side. Oops. So I have this, and on the right hand side I have sine squared theta O times what? I begin by copying these terms. 4 R naught to the 4, 27 Rs squared, minus RO squared plus Rs RO. And now I get these terms here. So on the other side they get a plus sign. I have plus RO squared minus Rs RO. And you see, this becomes very nice because these four terms cancel. And then I can solve for sine squared of theta O. Then I get, that was an RO here. Yeah, I think, I have here r to the 4 and here squared. I think I multiply this out, then I get RO minus RS. And from the other side, I have 27 RS squared divided by 4 RO cubed, right? Yes, that's it. And I think that's Singh's formula for what we now call the shadow of a Schwarzschild black hole. Well, it depends on what? Of course, it depends on the Schwarzschild radius, and it depends on where the observer is, on the RO. And you see, if the observer approaches the horizon, then what is this? It becomes 0. There's something wrong. Let's check. If the observer goes to infinity, then actually the shadow, the sign should become 0. It goes to infinity. Yes, that's true, because it's a higher power than in the. Oh yes, of course. The sign of pi is also 0. Yeah. Not only the sign of 0, also the sign of pi is 0. Yeah. And actually, we will discuss it in a minute. So if the observer is very far, then the radius is 0. If the observer comes closer, the radius becomes bigger, bigger, bigger. Then it reaches pi half, and it becomes bigger than pi half, and then goes back to 0. The sign goes back to 0, because the angle goes to pi, right? So if RO is equal to RS, then the sign is again 0, because then theta O is pi. Yeah, it covers the shadow covers the whole sky. So if you plot this, these famous diagrams with the escape cones, which you can find in many, many books. For instance, in Chandrasekhar's book on black holes, you find a picture of this sort. So if you are far away, so if you are RO, say, very big in comparison to RS, then what you have is that a tiny part of the sky is dark. Yeah? So this is a cone, and the opening angle of this cone, this is a theta O. Yeah? So you see a tiny dark spot in the sky if you are far away from the black hole. And then you come closer to the black hole. Let's say you are at 3/2 RS. That means you are precisely at the light sphere. If you are at 3/2 RS, then this expression should become 1. There's something wrong with the factors, right? 3/2. Oh no, I have it. Sorry, I also have it here. Yeah, I think it's true. Let's just check. If I have RO is 3/2 RS, then I have sine squared of theta O is what? RO minus RS is 3/2 minus 1 is 1/2, right? 1/2 RS. 27 RS squared, and 4 times this thing cubed. 3 cubed is 27 RS cubed, and 2 cubed is 8. And you see this is indeed 1. Yeah? So if you are at the light sphere, then half of the sky is dark. Yeah? So then half of the sky is dark. So your shadow covers just half of the sky. Yeah? So that's intuitively quite clear if you know what happens at this radius, namely that the light rays which are tangential stay on the fixed radius. Right? So these are just these boundary light rays here. And then of course you should stop before you reach the horizon. So if you are, let me write it in this way, if you have RS plus a little epsilon, then almost the whole sky is dark. Yeah? And if you really reach the horizon, if R is equal to RS, then the whole sky is dark. But then you are doomed. You are already at the horizon and you cannot escape. So that's the way in which you would see the shadow of a black hole under these idealized conditions. So what are the idealized assumptions which we have made? The assumptions are that light sources are not situated between us and the black hole. Yeah? So if you have light sources between us and the black hole, then you will have all kind of other things which block the shadow in a certain way. Yeah? So you wouldn't see this clear-cut circular shape. That was the first assumption, and the second assumption is that light moves on light-like geodesics, which of course is only true if there's no matter around, which would influence the light. So if you have scattering or something like that, which you expect to have near a black hole, then also this would be modified. So that's a highly idealized way to calculate the shadow of a black hole, but it's a starting point for all more sophisticated ways of discussing the shadow. And as I said, people think that the shadow really exists and that one should observe it, that it should be possible to observe it. And they are trying to do this with a black hole at the center of our galaxy quite intensively. There are two projects at the moment underway. One is called the Event Horizon Telescope and one is called the Black Hole Cam. Both cooperations try with fairly high financial effort with big radio telescopes to observe the shadow of our black hole. And with the help of Things formula, we can now quickly calculate how big actually the shadow of the black hole at the center of our galaxy would be, what you would expect. So if it is a Schwarzschild black hole, yeah, we have to be careful. Actually, we are fairly sure that it is not a Schwarzschild black hole. We are fairly sure that it rotates, and this makes things, of course, more complicated. We come to rotating black holes later. But for the time being, let us just assume, for the sake of simplicity, that the thing at the center of our galaxy is a Schwarzschild black hole. Then we would be interested in something which, with a Schwarzschild radius of what? What's the Schwarzschild radius we expect for the black hole at the center of our galaxy? Has 4 million solar masses.
4 million kilometers.
Yes. So the Schwarzschild radius of the sun is 3, so let's multiply with 3, so then we get 12 times 10 to the 6 kilometers. Yeah? So that's approximately what we expect for the Schwarzschild radius of the black hole at the center of our galaxy. And how far is this thing away? So what would be the RO? Nobody? Yeah, it's something like 8.5 kiloparsec. Actually, we know this number with much higher accuracy than this number. Yeah? It's surprising how big the inaccuracy of our knowledge of the distance to the center of our galaxy is. Okay, but we just want to estimate the order of magnitude. If you do this, where's Things formula? Here is it. If you just insert these numbers into this formula, then you find that what one usually gives is 2 theta O, that's the diameter. Yeah, the diameter of the shadow. You get something like 54 micro arc seconds. Micro arc seconds, yeah? 10 to the minus 6 arc seconds. Everybody knows what an arc second is? Yeah? No? Come on. But has also everybody an idea what it means in astrophysics for astrophysical objects? So for instance, the object which I usually mention for sake of comparison is Jupiter. I think most of you have seen Jupiter in a telescope, the disk in a telescope. This is something like 45 arc seconds. 45 arc seconds. Yeah? The diameter. And now you can imagine what this is. So with optical telescopes, it's absolutely hopeless to measure such an angle for the foreseeable future. Yeah, we are far, far away from this. But with radio telescopes, it is possible. And what's the reason? Why does it work with radio telescopes and not with optical telescopes? Well, because with radio telescopes, it's much easier to use interferometric methods. In principle, it can also be done with optical telescopes. Since a couple of years, this is done intensively, but it's much, much more difficult. And we have not yet reached this level of accuracy. So an angular distance in the sky of 50 or even 40 or even 30 microarc seconds in the sky can be resolved already now with very long baseline interferometry. So this is within the reach of radio telescopes. So I should emphasize it only works with radio telescopes actually for two reasons. The first reason is that this resolution cannot be reached with other kinds of telescopes. And the second reason is that we don't see the center of our galaxy with optical telescopes. Yeah? We see it with in a certain range of radio telescopes down to the infrared, in the far infrared. We can also make observations. Actually, these instruments I've mentioned, the Event Horizon Telescope and the Black Hole Cam, this will operate in the sub-millimeter range. So this is already in the infrared, yeah, at the borderline between radio and infrared. So, yeah, physicists usually call this far infrared. So radio astronomers call it sub-millimeter radio frequencies. So this is something which is tried now intensively, and well, if we see this dark disk actually at the center of our galaxy, then we do not know that the thing is a black hole. We do know that it has a light sphere, yeah, that it has this light sphere disposed to an external observer. So it could still be some of these, yeah, highly hypothetical ultra-compact stars. Even if we see the shadows, that would not be a definite proof that it is a black hole. But it would be a very, very strong indication. Because actually, I think everybody would agree that all candidates for these ultra-compact stars are much, much more exotic than a black hole. A black hole by now is for astronomers and astrophysicists a very commonplace thing. So they accept this now, since 15 years or so. It's a fairly recent development. But all these other things, all these candidates for ultra-compact stars, they are very much more exotic than a black hole. So in this sense, I think it would certainly be a very strong indication that we have a black hole at the center of our galaxy if the shadow would be seen. And what is the most intriguing thing is the question of whether it is really circular or if the shape differs from a circle. If it differs from a circle, and that's actually what you would expect, then this would be a definite proof that the thing rotates. Yeah? Because a non-rotating thing, a spherically symmetric thing, whatever it is, would have a circular shadow. So this was the issue of the shadow, which is under very vivid investigation at the moment. And well, we have now the mathematical apparatus to verify, at least for the simplest kind of black holes, namely for the Schwarzschild black hole, all the relevant formulas in order to calculate this. Okay, in the last 10 minutes or so, I will now say a few words about multiple imaging. So when we discuss multiple imaging, when we discuss the shadow, we assume that light sources are distributed more or less homogeneously everywhere except in the region between us and the black hole. When we talk about multiple imaging, we ask the question, how many images do we see from one particular light source? So we fix now one particular light source situated at a certain distance, say behind the black hole, and what do we see in the sky? Well, certainly we would see one image along this light ray which I've drawn here. From the same light source, what would you expect? Do we also see more images? More images than just one? What would you expect? At least for appropriately chosen positions of the light source. How many images would you expect? I see somebody making this motion with his hand, which is very, very telling. Yes. Yeah. Okay, so obviously there's this light ray, then maybe there's a second one, which goes on the other side. And then there are infinitely many more. Because a light ray can make one full turn. It can make two full turns. It can make three full turns, and so on. So actually there's a two-parameter family of infinitely many images. So what we have, if we fix now a light source. Let me write this at the radius RL. L stands for light source. And here an observer at RO. Here is our horizon, RS. Here is the light sphere, 3½ RS. What happens is the following. There's one light ray which goes this way. One light ray which goes this way. Then there is one which goes towards the light sphere, reaches the minimum, and then goes to the observer. And then there's one which makes 2 turns. 1, 2. And then goes to the observer, and so on. 3 turns, 4 turns, and so on. So there's an infinity of images. And the light rays come closer and closer to the light sphere. So this means the directions converge towards the thing which goes asymptotically towards the light ray. So it means it converges towards the boundary of the shadow. Yeah? So what we see in the sky is, here's a shadow, here's a shadow. Now I consider this particular light source. I see one image on one side. It corresponds to this light ray. And one image on the other side, corresponding to this light ray. And then I have this infinite family of light rays, which converges upon the shadow. Actually, if you do the calculation, if you do it really with the formulas, not just with your geometric intuition, you find that already the next image is very, very close to the shadow. And all of them clump together here very, very closely. And actually they do converge towards the shadow, but from the second onward you cannot distinguish them because they really clump together. And the same thing on the other side. Of course you also have these light rays here, which go this way. Yeah? So they give rise to a sequence on the other side. So you have an infinite sequence of images on either side. And that's another thing which would be very, very intriguing if it could actually be observed. These so-called higher order images have never been observed for any object in the sky. We don't know them. Yeah? Light rays, images which correspond to light rays which make a full turn around the center. We have no indication from observation that they exist. Theoretically, we are convinced that they exist, but we have never seen them until now. But the black hole at the center of our galaxy might also give a certain chance that we will sometimes see them. And what people hope is not that they resolve this infinitely many images, but that we see at least all these things together, clumped together at another image. Yeah. So this could be possible that one can just distinguish the higher order images clumped together in one image close to the shadow. If you do the calculation, you will also find that the intensity goes to 0. That's another issue. Yeah, so this is the brightest image. Then the next one is darker, the next one is still darker, and so on. And actually the intensity goes down dramatically. Yeah, so this is by far the brightest. And all these things together are not as bright as this single image. So there are two issues. First, it would be difficult to resolve them. And second, it would be difficult to reach the sensitivity which is necessary to observe them. So these are the two main features, the two main lensing features of a Schwarzschild black hole: the shadow and these infinitely many images which clump together on the near the shadow. And both phenomena have not been observed until now, but we are hoping that they will be observable. Yeah. Well, I've asked a colleague, a very prominent radio astronomer who is involved in this observation, how if he thinks that there's a good chance that they will be observed during our lifetime, and he said certainly in my lifetime. He's a couple of years younger than I am, so but actually I would also hope that I will live long along to see at least the shadow. Maybe not the multiple images, but maybe the shadow. Actually, I was talking here about now one single light source. If you have a distribution of light sources, this means that all these higher order images together give rise to a bright ring around the shadow. This is also something which could be observable. Yeah? If you have light sources distributed, say behind the black hole, more or less continuously, then all these higher order images together would be very, very close to the shadow, so they would give rise to a bright ring around the shadow. And this bright ring could also be visible. And then there's all this other rubbish around, if you have an accretion disk and whatever, which is in front of the shadow, yeah, at least partly. And this will of course block part of the images we have constructed here mathematically. Okay, so this is one of the most intriguing subjects in the field, in my view, observing the shadow and other lensing features of black holes. And at least for the Schwarzschild space-time, the calculations are fairly easy. Yeah, you can fairly easily verify everything you want to know. We will come back to this topic when we talk about the Kerr space-time, then it will be much more complicated. But I think I will also do a full calculation of the shadow for the Kerr metric on the board. This should be feasible. Okay, time is out. See you on Friday.